Hi there, this is GCSE Physics Space. This is lesson 4, and this one is orbital period. So if you're going to start with this one, start a question. So complete the following table. It says the first one has been completed. That's a lie, it hasn't. So, object is stationary with no resultant force. What will happen? So the object will simply remain stationary. Next one then, so what if there is a resultant force? So the object will accelerate in the direction of the resultant force. What about if the object is already moving? If there's no resultant force, the object will continue at a constant velocity in terms of its magnitude and its direction. And then finally, if the object is already moving and there is a resultant force, the object will accelerate or it will change direction. So it's either a change in speed or a change in direction. So an object that is moving at a constant speed and there's a resultant force on it and it changes direction but maintains its speed, you know, it's still changed its velocity and it has indeed accelerated. And we'll come on to that in the context of orbits in this lesson. So planets have elliptical orbits, which is basically a slightly squashed circle. And for this lesson and everything that we do, we'll approximate this to be a normal circle. So have you got any idea how fast the Earth is travelling relative to the Sun in a straight line as it's orbiting? It's around 1,000 miles per hour. So, you know, pretty quick. If you travel 1,000 miles an hour on the surface of the Earth, you wouldn't last very long. Obviously, for a spacefaring object, it's not massively fast, but it's still impressive. So a big question then: how do we stay in orbit? So I'm going to give an explanation. So the speed at which we're orbiting the Sun is constant. So we're travelling at a constant 1,000 miles per hour. However, the direction that we're going as we're orbiting the Sun is constantly changing. And remember, velocity is a vector quantity. So what that means is that it's got to have magnitude and direction. By magnitude, that just means the size. So velocity's got a direction. If we're constantly changing direction, that means our velocity is constantly changing. So as I've written there, since the Earth is continually changing direction as it orbits, its velocity is always changing. So if you've got a change in velocity as you're obviously moving through time, then acceleration is changing velocity over changing time. So it should have that equation, acceleration. So you can either write that changing velocity over changing time, or you can use the v minus u, so final minus initial over time. But if we've got change in velocity, change in time, that means we're accelerating. And we are accelerating. We're accelerating towards the centre of the orbit, and it's got a name. It's called centripetal acceleration. And the same applies for anything in orbit. So moons, artificial satellites, etc. So make sure you get that down. If you want to follow that explanation again, just rewind, watch it again as you're making notes. All right, let's move on. So remember, it applies to planets in orbit around the Sun, moons that are in orbit around their planet, and man-made satellites. So we've got the Earth there, we've got Luna, which is our moon. Remember, there's lots of moons in the solar system. Most planets have moons. And then the man-made satellite at the top is the new James Webb Telescope, which is also in orbit. Right, so another common question. So here's two satellites. The image on the right. So which one's travelling faster and why? So we've got one that's obviously in orbit closer to the planet. We'll say it's the Earth. And then the other telescope or satellite, whatever it is, that's further away from the Earth. So which one of those is travelling faster and why? So it'll be the satellite closest to the centre. By the centre, I mean the centre of orbit, so the planet. So the satellite closer to the planet will experience a stronger force of gravity. Therefore, it must be travelling faster so it doesn't fall into the planet. So basically, the closer it is, the faster it's travelling. And velocity is also inversely proportional to the time period. So the closer it is, the faster, you know, it takes, the quicker it is to orbit. So something in a low polar orbit that's very close to the Earth can travel around the Earth in around 90 minutes. As they get further out, you know, something that's a bit geosynchronous, which we'll talk about in a minute, you know, can take 24 hours. So the closer it is, its time period, the time period to orbit is less, and it is also travelling faster. All right, hopefully that's okay. So last thing, geosynchronous orbit. So geosynchronous orbit is a satellite will orbit at the same speed that the Earth rotates. So it'll also take 24 hours to, travel around the Earth as it moves with the Earth, so a full day. As you can see in the GIF on the image on the left-hand side, it's just rotating with the Earth. Obviously, that's sped up. So, and some uses for geosynchronous orbit are communications, mobile telephones, especially meteorology and GPS navigation. And that's about it. So that's a shorter one, but still job done. And thanks for watching.